right, calculus. I will be uploading your year-end assignment this week sometime. That will show up, so be on the lookout for that. So far for the homework, what people have asked for so far is number 8 on page 469. So I'm looking at number 8. I probably shouldn't have given you number 8, to be honest, because I didn't go over example 4, so that really wasn't fair of me. I'm sorry, I didn't actually look. I had the numbers written down, but it was for if I had done that example, which I didn't. So we'll go over it, no big deal. The population of algae in a fish tank can be modeled by P is equal to PO, A to the T. So that's the formula that they say this algae grows at. So the initial population is this one, and T is the time in hours, and it says at time 0, the population is measured to be 200. So at 0 hours, at time 0, that means the original population is actually PO. And it says determine the values, and at 3 hours, the population is 800. Now part A says figure out what is A and what is PO. Well, we've actually already done that just by reading the information, because they said at time 0 it's 200. So that's the original population. So that's actually already answered. So it really is just A that we need to find. So we know that the original population is 200. We know that when time T is 3, the final population is 800. So I really have 800 is equal to 200 times A cubed. So if I divide this side by 200 and I divide this side by 200, I end up with 4 is A cubed. So if I just take the cube root of this side and the cube root of this side, I get that A is 1.5874. And it keeps on going, but that's a significant amount of numbers, so we'll leave it there. So that's part A. Part B, how long will it take the population to double? So this time, I'm looking for a T. I have now figured out that A is 1.5874. So they want to know how long. They want to know a time, so T, when the population doubles. So if the original population is 200, that would mean the final population would have to be 400. A is 1.5874, and I'm looking for T. So again, I would divide. So T is equal to 1.5874 to the T. Now, when we're trying to find an unknown in an exponent, again, thinking back to Math 12, you actually have a couple of options. I could take the log of both sides and bring my T down in front. I could do that. So I could take the log of this side, take the log of this side, use my power rule, bring the T down in front. So I have T log of 1.5874, and then I could divide both sides by log of 1.5874. Or the other option would be, because this is a simple exponential function, The other option would be to change it from exponential form into logarithmic form. And to do that, this would be log, whatever the base of this is, that is the base of my log. And it would be log of 2 is equal to t. And we said if you want to evaluate a log in your calculator that is not in base 10, there was a shortcut for that. You do log of 2 divided by log of 1.874, which is what I ended up doing when I did it the long way, when I took the log of both sides and did the power rule. This is just a shortcut. Either way, I'm going to end up doing log of 2, and I'm going to hit equals there, divided by log of 1.5874, and I get that t is 1.5 hours, 1.5 hours. So that would be B. C. C is really where the derivative comes in, and again, I can put in some generic numbers here. I know that the original population is always 200. I know that A is always 1.5874. So there's sort of my generic formula. And it says determine the rate of change of the population after 1 hour and after 6 hours. So what I would have to do is I would have to do the derivative. So again, to do the derivative, I would take the ln of both sides. But if I'm taking the ln of this, I'm taking the ln of that whole thing, right? Think about your product, your log of your product rule for logs, which says if you're multiplying these two things and it's a ln or a log, you can say this is ln of 200 plus ln of 1.5874 to the t. We can do both. So then I can use my power rule to bring the t down in front. So I have ln p is equal to ln of 200 plus t times ln of 1.5874. All right, so remember that the unknown in this is time, right? So when I do the derivative, I am going to do the derivative of ln p. So the derivative of ln is 1 over p, but I have to say I did the derivative of p with respect to time because time is the unknown. It is the independent variable. Over here, the derivative of ln of 200 is 0 because it's a derivative of it's a constant, right? Plus, now here is f, here is g. I'm going to have to do the product rule with that. So g, which is ln of 1.5874, times the derivative of t, which is 1, plus t times the derivative of ln of 1.5874. Again, that's a constant, so that is 0. So what I end up with is 1 over p dp over dt equals ln of 1.5874. Okay, I need space again, so I got to go up here. Okay, so that's what I have so far. So I want to get dp dt by itself, so I'm going to multiply both sides by p. So I have dp over dt is equal to I'm multiplying this side by p, so that my p's cancel. So p times ln of 1.5874. All right, now p, remember back, I erased it, that wasn't very smart of me. Remember that p was 200, 1.5874 to the t, right? So I can replace p with 200 times 1.5874 to the t times ln of 1.5874. and that is dp over dt. That is the derivative. That is the rate of change. So they say determine the rate of change after 1 hour. So I'm going to put 1 in there for my time, and I'm going to evaluate. So if I put 1 in there for my time, then I end up with 200 times 1.5874 times, and I'm going to put brackets around this, ln of 1.5874, and I get dp over dt equals 146.8, meaning the rate of change of algae, the algae is growing by about 146.8 algae per hour after only 1 hour. But remember, it's growing exponentially. So what about after 6 hours? So I would do it again, but I would put 6 in for my time. So I would do 1.5874 to the 6 times 200 times ln of 1.5874, and I get 1,478.7. So after 6 hours, the algae is increasing by 1,478.7 algae per hour. So all of a sudden it's growing much, much quicker. All right. It says, will this model hold true for all time? Likely not, because the algae will run out of food to eat and then it will start dying off. The temperature will change. The algae won't be able to grow anymore. Different things will happen to affect how quickly the algae population is growing. But for those first 6 hours, it's ramping up, because after the first hour, it's only growing by like 146 algae. By after 6 hours, it's growing by 1,478 algae per hour. And again, that's not how many algae there are. It's how many it will increase by in that hour. All right. Last section in chapter 7 is the word problem section. So kind of more like this. So I'm just trying to decide what I want to do here. You'd think I would do that before I record, but no, that would, actually be useful. I don't do that, right? Okay, 1, 2, 3, and 7. Okay, so all of this is now they're moving to the application of this. So unless you see the words rate of change, you don't have to do the derivative. If you see the words rate of change, then you have to do the derivative. So I'm going to do 3 examples. And example 2 is actually the long one. The other ones are not nearly as long. So example 1, page 471. A population of 800 E. coli bacteria doubles every 15 minutes. So you have 800 E. coli bacteria to start with, and it's going to double in 15 minutes. That sounds terrifying. Determine the formula for the number of bacteria at time t. So again, this is exponential growth, so we're going with our standard formula of the population is equal to the original population, or your starting population, E, because it's continuous growth, to the K times T. K being your growth constant, T being your time. So we know that it doubles every 15 minutes. Now, the reason why they have told us that seemingly useless piece of information is so that we can figure out what K is. So if we're starting with 800 and it doubles, that means we end up with 1600. And it does that in 15 minutes. It does that in 15 minutes. Now, we're going to leave our time in minutes. If you were to change your time to hours, then your time would be 0.25 because 15 minutes is a quarter of an hour. We're going to just stick to it in minutes. It doesn't matter as long as you keep your time in the same units, it's fine. Just don't like all of a sudden halfway through your question switch from it being in minutes to it being in hours. Stick to one, all right? So if it's 15 minutes, again, I'm going to divide this side by 800. I'm going to divide this side by 800, so I have 2 is equal to e to the 15k. I would change this into logarithmic form. Log of e of 2 is 15k. Log base e is really just ln. So I have ln 2 equals 15k. So if I want to know what k is, I'm just going to divide both sides by 15. And if I do ln 2 and I divide by 15, I get 0.0462. So what that actually means is that the algae is growing by 4.62% every minute. Seems like a lot to me. So our K is 0.0462. So in the first part, when it says come up with like basically just a generic formula, now that we know what K is, we can give a generic formula. The population would be equal to the initial population, which for this is 800, e to the 0.0462, because that's my K, times however long we observe this for. So there is my generic formula for this specific E. coli bacteria. That's part A. Part B, interpret the value of K. I already did that for you. I said that that actually means this particular bacteria is growing by about 4.6% every single minute. That's really scary. So it means if you get infected, it's not going to take long. So how long will it take for the population to reach 10,200 cells? This is math that's like an epidemiologist would do because they would know things like when does someone start showing symptoms? Well, if they start showing symptoms when there's 10,200 cells in your body, then, and they want to know how long that's going to take, they would use this type of formula to figure that out. And they would know, okay, at that point, they're going to start showing symptoms. So it's been one of the problems they've had with COVID is that it hasn't been actually consistent for some reason. Some people show symptoms very early on, so very soon after infection, so when there's not a lot of virus in their body. Others like never show symptoms. And so why is that? Why do some people not show symptoms and other people do, right? These are some of the things that they're currently trying to figure out with COVID, because it's acting a little differently than some of the things that they've seen in the past. And so they're trying to work those things out. Again, it's a novel virus, it's a new virus, and so they have to learn about how this particular virus works. Well, this one that they're doing the example for is one they would assume we already know how it works. And so let's say that you were going to start showing symptoms when the population gets to 10,200 cells in your body, and you started out with only 800. How long, based on how quickly we know that this E. coli bacteria can grow in your body, how long before you start showing symptoms of infection? So for this, again, they're not asking for a rate of change. Those words have never come up, so we are not doing a derivative here at all. So in this one, I would divide this side by 800. I would divide this side by 800. And I have 10,200 divided by 800 is 12.75 is equal to e to the 0.0462 t. So again, I would change this into logarithmic form. So log e, also known as ln, of 12.75 is equal to 0.0462 t. So I'm going to divide this side by 0.0462. So I'm going to divide this by 0.0462. So I'm going to go to my calculator. Log e, remember, is just ln. So ln of 12.75, and I hit equals so that I know I have that answer. And then I just hit divided by 0.0462, and I get that t is 55.1. And remember, we said we worked our time in minutes. So in under an hour, those 800 E. coli bacteria have grown to be 10,200. Very fast growing bacteria, whatever this is. All right. So we're actually going to go into what I will call CSI mode now. We're moving away from bacteria, and we're moving into CSI and crime scene mode. It's a morbid one today. I don't know why. Goes with the headache I have, I guess. All right. Excuse me. I really do have a really bad headache, so if I start saying things that don't make sense, sorry. All right. Example 2, forensic medicine. I'm going to read I'm going to paraphrase. Probably not going to read the whole thing. I'm going to paraphrase the paragraph above example 2, and then we're going to talk about example 2. Like I said, this one is the one that is going to take the longest to do. Don't worry about it too much. It's not one that's going to show up like on a test or on like, I was going to say exam, but we're not doing one of those. But it won't show up in one of those because I wouldn't have you memorize the formula. Okay? So, the cooling of any object, how fast something cools down, can be modeled by an exponential decay question. So just like exponential growth, this is exponential decay. So really the only difference between exponential growth and decay is that value of k would turn out to be negative if it was decay because it's breaking down, instead of that k being positive when it's growth. All right? Now, according to Newton, yes, Isaac Newton, like from physics, according to Newton's law of cooling, the difference between the temperature of an object and the temperature of its surroundings decreases exponentially according to this formula. So, we know that normally the formula is P is equal to POE to the K times T, right? That's our normal formula. So, but we're not talking about population, we're talking about temperature. So if that were the case, then the normal formula would be T is equal to TO. But because Newton said it has to do with the difference between the temperature of the object you're observing and the temperature of its surroundings, then it's really temperature minus the surrounding temperature is equal to the original temperature minus the surrounding temperature, E to the K times T. So really the only difference, people freak out because this looks more complicated, but the only difference really is that to both of these, you are subtracting your surrounding temperatures. We're actually going to talk about dead body here. So if you've ever watched, I usually reference CSI, but CSI is not really on TV, but any of those crime shows where the coroner shows up to the crime scene, and he has to estimate how long the person has been dead. What they do is they take the temperature of the dead body's liver, because they know, based on this law, if like a normal body temperature should be versus what the actual body temperature would be. But they also know that that can be affected by where is that dead body. If you find a dead body in the middle of winter in Nunavut, that's very different than finding a dead body on a beach down south in Mexico somewhere, right? You start off at different temperatures. The surrounding temperature is different, right? That dead body is going to cool down a whole lot faster if it's in Nunavut than if it's in Mexico. And so you have to take that into consideration. Go back to something not quite as morbid. Go back to something like a cup of coffee. If you have a cup of coffee, or in my case, tea or hot chocolate, if I'm feeling not fat, but right now, oh my word, are you guys eating like everything? Like, you're gonna have to roll me out of the house soon. I really need to get out, and the gyms really need to open. Anyway, sorry, I just tangent. Okay, too many drugs. I mean Advil, not bad drugs, just Advil. This is YouTube. So, if you have a cup of coffee, cup of something hot, right, and you have it again on a beach in Mexico, your cup of coffee is going to stay warm for a fairly long time. However, if you take your cup of coffee outside in the middle of winter in New Brunswick, your coffee's not going to stay hot very long. It's why they have spent tons of money developing cups like my Contigo that will keep things cold or hot for long periods of time, no matter the surroundings. All right, so we're actually going to look at this, what I call CSI, crime scene investigation, but this forensic question. All right, and I apologize. Yes, I know they're talking about dead bodies. It's okay. If you were going to go into forensic science, these would be the types of questions that you would be learning how to deal with. Just a second. All right, so it says the temperature of a recently deceased body is found to be 28 degrees at 3:30 p.m. So the temperature of the body is 28 degrees at 3:30 in the afternoon. So the coroner has come to the location where at the crime scene, he's taken the liver temp. It's 28 degrees at 3:30. And by 4:30, the temperature has gone down to 25 degrees by 4:30, okay? The air temperature in the room, so the surrounding temperature, is 20 degrees. So they probably found this in a house somewhere, right? Assuming that the body temperature was 37 degrees when he was alive, because that's normal. Again, I have actually seen episodes. I saw an episode, I can't tell you what crime show it was now, but I do remember there was one episode where they were trying to pin it on this guy, and everything looked like it was this guy who had committed the murder, and all the evidence was pointing to him, and the time of death worked, and he kept saying, I'm innocent, I'm innocent, I'm innocent, I didn't do it. But the coroner kept saying, no, I'm telling you, time of death was like 2 p.m. and he was there at 2 p.m. and so it had to be him that was doing it. He kept saying, I'm telling you, like, it wasn't me. Turns out that the person was actually sick and had a fever when they were killed, so that threw time of death off, because he didn't start off at a normal body temperature. And so when they determined time of death based on how quickly they know the body cools down, they were off by like an hour or 2 hours or something. And so by that point, the guy had gone and the real murderer was there and had committed the crime. And of course, you know, within the hour, they had wrapped up the whole thing. But I remember that because that episode happened right when I was teaching calculus, and I went, oh, that's a perfect example. So the question is, when did this person die? What is time of death? All right, so we are now coroners for the police department. We have gone to a crime scene. This is the information we have. When did the guy die? All right. Some year I should like set up a crime scene and have people do this question. Anyway, so I'm going to go through this step by step, okay? So we're going to assume that Newton's law of cooling applies. We're going to assume the guy wasn't sick when he was killed and his body temperature was normal, and that he wasn't me, whose body temperature is like a degree less than everybody else's. So first, we use the given information to determine the value of K. All right, so we're going to determine the value of K. So here's how we're going to do that. So, first thing they do is they do this. They say it's temperature minus surrounding temperature. So whatever the temperature of the object, the body was, we're going to be subtracting the surrounding temperature, the temperature of the room, which is 20 degrees, is equal to the original temperature. And when he was alive, that would have been 37 degrees, minus the surrounding temperature again, which is 20, e to the k times t. So if we just condense that down a little bit, we end up with t minus 20, and 37 minus 20 is 17, e to the k times t. Now what they do is they isolate t for temperature, and they move this 20 over here. So they have t is equal to 20 plus 17 e to the k times t. All right. Now what they do is they set up a system of equations using this information up here. So I'm just going to come back to here for a second. So here's what they do. We have two temperatures. We have 28 degrees and we have 25 degrees. All right. So if we set up 28 degrees, the temperature is 28. That's equal to 20 plus 17 e to the k times t. And we're just going to leave t as t for the moment. I'm going to show you why in the next one. An hour later, okay, an hour later, the temperature has changed from 28 down to 25. 20 plus 17 e to the k. Now here's where we're going to change, okay? If t represents 330, then 430 would be t plus 1, because it would be that time of 330 plus 1 hour. All right? Okay, so now what they do is they simplify this a little bit. Okay, they simplify these two equations a little bit, and they move the 20 back over here. So I have 28, take away 20, that's 8, is equal to 17 e to the k times t. And if we bring the 20 over here, we have 25 minus 20, which is 5, equals 17 e to the k times t plus 1. All right. Now, what they do with this they divide the second equation by the first one, okay? So they actually divide, they don't divide this one by this one, they divide this one by this one. I'll show you why in a sec, okay? So they do 5 over 8, 5 divided by 8, you could make that a decimal if you want. 17 over 17 would cancel, okay? And then what we do is we actually subtract. Yeah, we actually subtract, okay? So it would be e to the k, and I would be subtracting t plus 1 minus t. I would be subtracting those two. So my t's would actually end up canceling, and I would have 5 over 8 e. Now remember, this is multiplying, right? So I would have k times 1, which would just be 1. Sorry, not 1. It would be 1. It would just be k. 1 times k. All right. So I have 5 over 8. So all I did was I divided this by this. So 5 divided by 8. They didn't bother to make it a decimal. They just left it as a fraction. 5 over 8. 17 over 17, that cancels. E over e, we're going to actually just subtract here, okay? We subtract our exponents, which just leaves us with k when we subtract our exponents. All right, so then what they do, remember we're trying to figure out what k is. So if we're trying to figure out what k is, we can change this into logarithmic form. So log base e of 5 over 8 is k. Now remember, log base e is just ln. So I'm going to do ln. If I can turn my calculator on, I'm going to do ln of 5 over 8, and that is k is negative 0.47. Makes sense that it's negative because remember the temperature is decreasing. So it makes sense that the growth constant is a negative. So we'll put that up here. K is negative 0.47 because we've just figured out a piece of information. Remember, what we're trying to figure out is, when did this guy die? That's what we're trying to figure out, okay? So finally now, we find the value of t at 3:30 by substituting the value 28 for t, okay? So we're going to go back to here. We're going to go back to here because this one has t plus 1, which is pain. So we're actually going to go back to here, okay? And now we know what k is. So if I do, so I'm going to substitute in here. I got 28 is equal to 20 plus 17 e to the negative 0.47, because I now know what k is, to the t. And if you're not sure why I'm doing that, just a second and I'll explain, all right? So I'm going to move the 20 over here. 28 minus 20 is 8, is equal to 17 e to the negative 0.47 t. So I'm going to divide this side by 17. I'm going to divide this side by 17. So I have this. I would change this into logarithmic form. So it would be log e, which is ln, of 8 over 17 equals negative 0.47 times t. Now I'm trying to figure out t, so I'm going to divide this by negative 0.47, so I'm going to divide this by negative 0.47, and I'm going to find out that t and I could look, but I want to make sure I'm doing it right. 8 over 17 divided by negative 0.47, I get 1.6, which is right. So time is 1.6 hours. So what is that telling me? What have I just figured out in all this mess of numbers? What does that actually mean? Remember, the formula I was using here was for 3:30 in the afternoon. At 3:30 in the afternoon, the time is 1.6 hours since his temperature has been 37 degrees, the temperature of someone when they're alive. So that means this guy has been dead 1.6 hours, so a little over 1.5 hours. So we can put his time of death at just before 2:30 in the afternoon, or sorry, just around 2 o'clock, so 1.5 hours, not 1 hour, right around 2 o'clock in the afternoon. So if I am the coroner, I am telling the police officers, look for someone who was around at 2 o'clock in the afternoon, because that is most likely when this guy died. All right? So that was the long one. And again, I'm not going to be asking you to do something like that on a test or anything. But I do have at least one of those in your homework. So just, you can follow that step by step. I would even have the video going as I'm doing the question. All right, example number 3 is the last one. Now, I don't necessarily agree with everything that's stated in this question. We do it for the math portion. Just a sec. Carbon-14 dating is a radioactive substance that they say has a half-life of 5,730 years. So it has a half-life of 5,730 years. How they know that, I don't know. That's kind of where I go, really? I'm not sure how they know that or how they believe they know that. I also question, okay, yes, in today's atmosphere, but what was the atmosphere like years and years ago? Don't ever say that to an atheist, though. They'll jump all over you. So it is used to determine the age of artifacts. So you've heard about carbon dating. That's what this is talking about, is carbon dating. I don't actually agree with everything with carbon dating. There's some fallibility there. You can look it up. Hopefully you've done some of that in biology when they talk about the evolution part and everything. I hope they talk a little bit about that. But there are some questions surrounding carbon dating. So an archaeologist discovers a burial cloth of an Egyptian mummy has 45% of the carbon-14 that it contained originally. Again, how do they know how much carbon it had originally? I don't know. How long ago was this mummy buried? That's the question. So we know the formula is P is equal to POE to the K times T. Now again, at no point do they ask about rate of change. Notice I haven't done derivative in this section at all. Nowhere have they asked me about rate of change. Nowhere is there a derivative. So we're going to use this formula. First, we're going to determine the value of K because we know the half-life. Okay, we know the half-life is 5,730 years. So I don't know what the original amount is, but I know that the final amount, if we're talking about half-life, the final amount is half of the original amount, e to the k times time, and the time for the half-life is 5,730. So I have a PO on this side, a PO on this side, those will cancel. I have 0.5 is equal to e to the 5,730k. Change that into logarithmic form, so I'm going to have ln of 0.5 is 5,730k, And so I'm just going to do ln 5 divided by 5,730, and I get negative 1.21 times 10 to the negative 4th. That is K. All right. Now remember, we're trying to figure out how old is this mummy that they found in an Egyptian tomb. So now I know that K is 1.21 times 10 to the negative 4th. So I'm actually looking for time. So we're going to do something very similar to what we just did, because they said that when they found this, it had 45% of the original amount of carbon. So it had 45% of the original amount. Half-life, we put 0.5. So 45%, we're going to put 0.45. Again, those are going to cancel. I have 0.45 is equal to E. Oh, I need to change this up here because now we know K, hi bud, is 1.21 times 10 to the negative 4th times T. T is what we're trying to find. Hi, do you want to say hi? Come here, you can say hi. Rolly came upstairs just to say hi to everybody. Say hi, old man. Say hi. Say hi. Do you see? Do you see? Yeah? I'm not sure why you came running up, but good to see you. Can I put you down? He's going to cough now because he's really old and he has a bad heart. And when you pick him up, there he goes. He's going to cough. All right. So E to the 1.21 times 10 to the negative 4th T. And now my husband's chasing him around the room. It's very interesting. All right, so we're going to change this into logarithmic form. So we're going to have ln of 0.45 is 1.21 times 10 to the negative 4th times T. So we're going to do ln of 0.45 divided by 1.21 times 10 to the negative 4th. Turns out it's 6,600 years. So again, if you're an archaeologist, this is the type of math that you're doing. Yes, there's math in archaeology. There's actually quite a bit of math in archaeology. So according to them, they would label this at 6,600 years. I do have some questions about carbon dating. Not even that I'm trying to be a skeptic. I just don't actually know the answer myself. And I did see like a documentary, and they had like an old hat. And the people knew, like, the people who were putting it in to be carbon dated knew how old the hat was. They knew it was only around 40 or 50 years old. But when it was carbon dated, it came back as like 200 years old. But they knew it wasn't that old. So just kind of interesting that the math, even at that young age, and I don't know whether it was because it was young that they said that's what accounted for the discrepancy. I don't really know. Like I said, I don't actually know a whole lot about carbon dating, but I do have questions. I should look it up. I should really do some research. I'm hoping that perhaps you've done some of that in biology. We have officially finished chapter 7. We're not doing a test on chapter 7. We will do a test because we didn't really do a whole lot in chapter 7. We will do a test when we have finished chapters 7 and 8. Again, we're going to skip a bunch of chapter 8 because a lot of it is that terrible word trig identities. You already did them. We're not going to do them again. Yay! We're actually going to do 2 sections in chapter 8. We are going to do sections 8.3, which is on limits. And we won't really spend a lot of time there. And then 8.4, which is derivatives of sine, cosine, and tangent. We're going to spend some time there. And specifically, there's a couple of questions that we answer that takes into account literally everything we've done. And so I want to get those done. I suspect by the end of next week we should be finished, but by the end of this week I am going to have that assignment that will be due June 5th. I will have that up for you. I am working, I've got 2 classes done. I have 2 others, which calculus is one of them. I have 2 others I'm working on, and I want to get those done and up. That is top priority for me right this minute. Okay, I think I'm done talking. Thankfully, I'm gonna go. Actually, the drugs that I see, I shouldn't say that, should I? The Advil is starting to work now, so I'm feeling a little better. But I'm going to go and upload this to YouTube. So have fun watching my ramblings. Bye.